To pull the address resolution protocol cache, the command is exactly show ARP. But the agent inexplicably alters the syntax. It drops the correct instruction and instead executes show run, dumping the entire running configuration of the router. The system threw absolutely no error flags. The code executed. The failure was entirely silent, and the agent attempted to continue operating off of a massive incorrect data dump. A short context smoke test or a standard benchmark eval will give this model a passing grade. Those tests mask logic failures that only materialize when you deploy into long context production environments. The evaluation score printed on a model card describes the behavior of the raw weights in a laboratory vacuum. What you actually deploy is a completely different piece of software. Your production logic is governed by 3 distinct variables: the attention kernel, the cache format, and the GPU count. To isolate exactly how much damage these variables cause, an independent researcher ran a 100,000 token stress test on a single RTX PRO 6000 Blackwell GPU. The baseline software stack was strictly defined, the official unquantized Qwen 3.6 27 billion parameter checkpoint, running in BF16 precision through a pinned nightly build of VLLM. Against that unquantized baseline, the test introduced NVIDIA's own first-party NVFP4 quantization format to see if it could maintain logical coherence deep into the prompt. This chart tracks token divergence. As context length increases, the NVFP4 format chooses entirely different tokens. By 88,000 tokens, it suffers a 50. Contrast this with the bottom stable line, a third-party ADN-T8 W4A16 format retaining near-perfect fidelity. That highly accurate third-party INT8 explicitly used no calibration dataset during quantization, yet it easily outperformed the first-party FP8 release. The foundational weights were identical. The quantization format alone decided whether the agent typed the right command or broke the operation. So if we lock the weights, the cache, and the activations strictly at BF16 precision, the output should be identical every time, but the models still diverge. To find out why, we have to isolate a single changing variable during prefill, the attention backend. This diagram maps an inference stack processing a prompt through 3 parallel backends: Flash Attention 2, Flash Inference, and Triton. Initially, all 3 output the exact same math. Then, triggered by specific prompt content, the backends split. Flash Attention 2 outputs a different token. That single token flip cascaded. Flash Attention 2 altered the target network interface from Gigabit Ethernet 0/0/1.201 to Gigabit Ethernet 0/1/4, breaking the tool call. It is easy to assume this is just stochastic noise or random seed variance inherent to large language models. It is not. Rerunning the exact same attention backend produces logits that are bit-for-bit identical at every single hidden state. This divergence is a strictly deterministic byproduct of the specific matrix multiplication and addition operations hard-coded into the prefill kernels. The attention backend dictates prefill accuracy, but we also have to account for the KV cache. In the next test, the weights are held at BF16, but the cache is quantized to INT8. The reduced precision immediately triggers a tool call error, but because it is INT8, the cache retains enough precision to absorb the error. The model corrects itself, closes the tool call, and succeeds. When the cache is squeezed down to INT4, that recovery mechanism vanishes. The model fails to close the tool call entirely and loops into failure. The final physical variable is tensor-parallelism, how you distribute the workload across multiple GPUs via interconnects like NCCL. Running this identical test on a single GPU at tensor-parallelism 1 produces an acceptable and successful tool call. Take that exact setup and spread it across 2 GPUs at tensor-parallelism 2, and the tool call just completely fails. Increase the distribution to 4 GPUs at tensor-parallelism 4, and the tool call mysteriously succeeds again. The physical hardware topology, combined with cache precision, directly dictates the boundaries of a model's logical reasoning capacity. Beyond hardware and cache, the methodology of the fine-tune itself introduces severe breakage. We can see this clearly in uncensored or obliterated derivatives of the newer Qwen 3.8-27b model. This table tracks derivatives across a multi-tool evaluation range. The Heretic ARA tune shows a stable 0.7% flip rate, proving careful safety ablation won't destroy logic. But with the Aeon 7 tune, the flip rate jumps to 3%, causing 36 invalid branch futures. When an agent is writing operational code, a 3% error rate translates to destructive literal copy failures. At one point in the trace, the Aeon 7 model attempts to specify the standard PostgreSQL port, 5432. It corrupts the text string, generating 543QL, and fails the API call. Cryptographic hashes confirm that the vision and MTP tensors for these models match the base weights byte for byte. The uncensoring process directly damaged the core language weights. If you want to see the complete data readout on these fine-tunes the moment it drops, make sure you are subscribed to the channel. Techniques like obliteration routinely cause silent collateral damage to exact copy technical tasks and literal syntax. We need to apply severe methodological rigor to the data we just reviewed. The explosive metric from the first test, the 50% token flip curve on the NVFP4 format, requires strict context. That specific figure was generated by sampling logits only once every 32 prompt tokens. That is a total sample rate of just 3%. The researcher who gathered the data explicitly warns against relying on it, stating that a 3% random sample is an incorrect overall methodology for judging a model's total capability. Furthermore, that entire failure trace is based on a single prompt. Viral charts often mask fragile sample sizes. Relying on them blindly to architect enterprise infrastructure is an immense operational risk. Finally, we have to address how the evaluation metric defines a disagreement. Throughout these tests, the BF16 run was used exclusively as a numerical fidelity baseline. It was not graded as a guaranteed oracle of ground truth correctness. A token flip was recorded as a disagreement, even in instances where the quantized model selected a semantically superior token to the baseline. Because the test lacks semantic grading, it measures strict mathematical deviation, not definitive intelligence loss. Mathematical divergence guarantees your production stack will behave differently than your evals, but it is entirely on the builder to rigorously test if that difference destroys their specific workload.